In this video, we're going to take a look at trends involving ions. Before we take a look at that trend, we need to review what ions are very quickly. So, as you remember, atoms can gain or lose electrons, and when they do that, they become charged. So, a neutral atom can lose electrons and become positive, and that's called a cation, or it can gain electrons and become negative, and that's called an anion. Remember that generally metals tend to lose electrons and they form the cations, whereas nonmetals tend to gain electrons and they form, well, negative ions, the anions. And also remember that because noble gases already have their full valence shell, they don't really lose or gain electrons typically, so they generally don't form ions. So that was a quick recap as to what ions are, and that'll help us when we're taking a look at the trends involving ions in our periodic table. So you can probably spot the trend yourself. Let's take a look at these carefully. Here we have sodium, the atom. Here we have sodium, the ion. And this is, you can see the radius here, 154 picometers, 116 picometers. Here we have magnesium, the atom, and a magnesium, the ion. And we can see also 130 for the atom, 86 for the ion. So when you're looking at a metal turning into its ion, what tends to happen to the size? Right, it goes down in size. We have a smaller radius for the ion of that neutral atom. Same thing for the magnesium. Think about why that is. Think about what factor might explain that when it comes to these sizes. Now look over here. Here we have fluorine. Here we have chlorine. These are both nonmetals. They're both forming ions. And when they form ions, look what happens to the size of nonmetals as they become ions. The nonmetal size, the nonmetal ion is larger than the nonmetal neutral atom. So chloride is larger than chlorine. Fluoride is larger than fluorine. Think about why that is. But at least we spotted the trend. Metals get smaller when they become ions. Nonmetals get larger when they become ions. And so that's our general trend for the ionic radius. So the ionic radius is kind of like the atomic radius, but for an ion. It's the distance measured from the center of the nucleus to the outermost electron in an ion specifically, as opposed to a neutral atom. And so our first trend is that the cations are smaller than their corresponding atoms. So, for example, here we have lithium is smaller. The lithium ion is smaller than the lithium atom. The sodium ion is smaller than the sodium atom. So that's our general trend for that. And the reason that is because when you lose the metals, when they lose electrons, now the protons can pull the outer electrons closer to themselves because there's fewer shells. Remember, when metals lose electrons, they're losing the electrons in their valence shell. So they're basically losing a whole shell of electrons. And so there's fewer shells there, and we can pull in the remaining electrons closer to themselves. We can spread that positive charge over fewer electrons and pull them in closer and make the ion smaller overall. Anions tend to get larger, though. And so if you take a look over here, we have oxygen and the oxygen ion, which is larger than the oxygen atom over here. So the reason that is that we're adding electrons to the outer shell. Those electrons tend to repel each other away a little bit more. And also now the protons need to pull not just, 6 electrons, but 2 more electrons as well. So that positive charge has to pull even more electrons closer to itself than it did before, which is harder to do. And so there's less of an effective nuclear charge as a result of that. That's why the ion of a nonmetal is larger than the nonmetal neutral atom. And so you can take a look at the patterns here. If you're comparing just the ions, so for example, lithium to beryllium to boron, they still get smaller as you go from left to right, as you saw there. And that's because, again, even they have a positive charge holding on. You have more of a positive charge as you go from left to right. So the trend applies that way as well. But where it gets a bit tricky is now if you're comparing all the ions, the oxygen ion is larger than the boron ion. And that's because you have more shells because we gained electrons rather than lose electrons. So be careful there. The trend sort of swaps when you're comparing all the ions in there. But really, we're just going to compare, for the most part, the ion to its atom. And sometimes you can also ask to compare across groups and down groups as well. And we'll take a look at that in more detail afterwards. So let's just take a look, see if we understand the concepts. We'll do a few practice problems together. And then what you can do is you can try it out yourself. You can pause the video, and then check your work afterwards. So let's go ahead over here and take a look at the ionic radius. So ionic radius, again, is the distance from the center of the nucleus to the outermost electron in an ion specifically, not in the neutral atom. Cations will generally be smaller than their corresponding atoms from which they're made from. So for example, Na plus will have a smaller radius than Na because you lose electrons, you lose a shell, and as a result, you have a smaller radius because you have a stronger attraction by the positive charge that's pulling those outer electrons. Anions are generally larger than their corresponding atoms. So, for example, the F minus anion is larger than the F atom. And that's because when you gain electrons, there's more electrons than protons. And the nuclear attraction, because there's more electrons to pull in, is just not as effective as it was before. And also, some of those electrons are kind of repelling each other a little bit more. But it's really because now you have more electrons than protons, and you have more to manage than before. So let's take a look if we can answer some of these questions. So which atomic radius is smaller? So here we're dealing between S2 minus and S. This is an anion. We're comparing anions now. The anion is larger than the atom from which it's made. So that means the smaller one in this case is sulfur. Now in this case here, Mg2 plus and Mg, we're dealing with the cation trend. The cation is smaller than the atom from which it's made. So in this case, the Mg2 plus is smaller. In each pair, which radius is larger? So let's look at A. A, we're comparing the atom to its cation. And remember, the cation is always smaller, so the atom is larger. B, we're just comparing carbon and oxygen, the neutral carbon and oxygen. So let's go to our periodic table over here. Carbon and oxygen. Oxygen is more towards the right within the period, so oxygen is a smaller atom. Now here we're comparing Cl minus and argon. And that's a bit interesting. So let's go take a look at a periodic table, Cl minus and argon. So generally, if you're comparing Cl and argon, Cl is larger because it's to the right of argon. Now we have Cl minus, and Cl minus is still larger because Cl minus is even larger than Cl, right? Because it's the anion. So even though the question was asking this, just to clarify, Cl itself, the regular atom, the neutral atom, is larger than argon. And we know Cl minus is larger than Cl, so that means it has to be larger than argon. So Cl minus, chloride ion, is larger than argon. So let's go ahead and try these type of questions here where we have to rank the substances. So we have argon, chlorine, K plus, and S2 minus by decreasing radius. So what that means, we're going from the biggest to smallest. So let's do kind of what we did before. We're going to start just ranking a couple at a time and see if we can place them as we go. So we already know one of these pairs here, chlorine and argon. We know that chlorine is going to be larger than argon. So I'm going to go in that direction there. I'm going to put my larger ones more towards the left side. Actually, I'm going to rewrite this and save some room because there might be something larger than chloride. I don't know. So let's take a look. So chloride here, argon here. Let's go compare other things. Let's go see if we can compare some S. So if I was comparing S to chlorine, S, the atom, is larger than Cl, the atom. So that would mean that the trend still applies here. So the ion of sulfur should be larger than the ion of chlorine because the ion of chlorine would have more protons holding the electrons closer to itself. So the trend still works in that direction. So sulfide would be larger than chloride because it's to the left of the chloride ion. So I would go ahead and put the sulfur 2 minus over here. And now I just really have to look at K plus and see how that works out. So this one's a bit interesting. So we have K plus over here. And generally, we would say that that K plus, that K is a larger atom than argon because there's more shells. Generally, we'd say that. it would have one more shell. But we're looking at K plus now. So K plus is when K loses an electron. It loses its valence shell. So if it does that now, K plus has lost its outer shell. So it has the same number of outer shells as argon in this case. It really has the same number of electrons as argon. So you'd think, okay, maybe they're the same size. But when you think about it, potassium should be smaller than argon because they have the same number of electrons, but potassium has more protons still, 19 protons. It has a positive charge and is pulling onto those electrons even more than before. So because we're dealing with the potassium ion, it's going to be smaller than argon since we have the same number of shells, since we lost an electron, and we have more protons holding onto it and pulling it closer to itself. So potassium really is going to be the smallest thing here, the potassium ion. And we can write that S2 minus is larger than chloride, which is larger than argon, which is larger than K plus. So that's the way to approach a question like that. So let's try this one next. We have I minus, xenon, CS plus, and Ba2 plus. Let's go see if we can figure any of these out right now. So I'm going to compare CS and Ba. I'm going to try those first. Let's see. Here's CS and here's Ba. Generally, we know going from left to right, the size will decrease. And so that trend will still apply even if we're dealing with the ions. The size of CS and Ba ions follow that same pattern. So Ba is smaller as an ion than CS is as an ion. So Ba is smaller there. Now we are going from decreasing radius, so larger one first, biggest to smallest number. So CS plus is larger than Ba 2 plus. Let's compare other things. Let's take a look at where xenon would fall compared to those two. So xenon's over here. And this is kind of like the previous question. So generally, these would be larger than xenon because they have more shells. But when they become ions, Ba2 plus and CS plus, which is what's in the question, they lose their shells, their outer shell. And so they have the same number of shells as xenon now. And so what that means is that they're smaller than xenon because they have the same number of shells as xenon, but they have more protons and that positive charge pulling the electrons in even closer than xenon. Xenon has fewer protons, and it doesn't even have a positive charge to pull those electrons in very closely. So xenon would be larger than those two ions. So we'll have xenon over here. But we don't know if xenon is the largest yet. I still need to compare it to iodine, and it's iodide actually. It's the I minus. So if we go over here, generally iodine is larger than xenon anyways because it's more to the left. And as you know, iodide will be larger than iodine. So if iodine, the I, is larger than xenon, well, the ion is larger than the regular atom, then the ion must be larger than xenon as well. So the ion is larger than xenon, which means that iodide is the largest one here. So that's larger than xenon, larger than CS plus, larger than Ba2 plus. So that would be our arrangement in decreasing order of ionic radius and atomic radius. We kind of have both of them together here because this would be the atomic radius because it's not an ion, arranged that way. So again, you do need to think a little bit. Typically, when you have a metal losing electrons and forming an ion, it's going to be smaller than the noble gas that came before it because it'll have the same number of electrons now with more protons holding it closer because they got rid of their outer shell. And so now they'll just have the same number of shells as they had in the previous example here, or in the previous period here. So for example, strontium and rubidium would be smaller than krypton, just because they have the same number of shells now, but more protons holding them in. Within a period, if you have ions form, so the rubidium ion is still larger than the strontium ion because the strontium ion has more protons pulling itself in, so that effective nuclear charge still applies to the ions as well as you go forward that way. In the next video, our next trend we'll analyze is the first ionization and successive ionization energies.